Okay. All right. Hi, everyone. So today it's my pleasure to introduce Kasia Wyczesany, and she will speak on almost Euclidean and well-complemented subspaces of finite-dimensional norm spaces.
I'm just now realizing, thank you, Florian. Thank you for inviting me here. It's a pleasure. I'm just now realizing now that I made a different title on my slide than what I've originally announced, but I'm talking about the exactly same thing. I'm talking today about the joint work with my PhD supervisor, Tim Gowers. Let me start by saying, please do interrupt me at any time if I'm being unclear or not precise enough, or if you have any questions. And yeah, let me begin. So I will start right in with some introduction and definitions. In particular, I'll explain the notions of almost Euclidean and well complemented, as in the title that was sent to you originally. Then I will introduce a question that Vitaly asked. We haven't found it anywhere written down in any paper or anything, so it's just from a sort of personal correspondence between Tim and Vitaly. And then I'll propose a reformulation of the question, a reformulation of the strengthening of the question already, and introduce you to our main theorem, and then focus to try to explain you what are the main elements of the proof. Because I mean, paper on its own, it is quite technical, but I'll try to tell you a story of how one can attack a problem like this. Okay, so let me begin. Definition that probably all of you know well, the definition of the Banach-Mazur distance between two normed spaces X and Y of the same dimension is defined as the infimum over constant C, such that there exists an invertible linear map T from X to Y, such that this inequality here holds. That means that the image of T in the norm of Y is between the norm of X in X and the C times the norm of X, okay? Which means in particular here that a convex body that corresponds to the unit bow has an image which lies between two multiples of the other body. So if this is the unit bow, Euclidean unit bow of the space Y, that would mean that there exists a unit bow of X here and a unit bow of X here, which is a scaled one. So this was Bx, this is By, and this is C times By. Sorry, I'll start writing nicer in a moment. Right, and in particular, one is interested in the space X being L2, being the Euclidean space, and therefore here is a little definition. I'll be referring to spaces whose Banach-Mazur distance from the L2 space is a constant. I'll be calling those spaces C Euclidean, okay? All right, so a famous theorem, whenever you hear Banach-Mazur distance, your thoughts probably immediately go to the Vertsky Theorem, which states that there exists n, which depends on k and epsilon, so that for every normed space X of dimension at least capital N, one can find a k-dimensional subspace of E such that it is almost like L2. Its Banach-Mazur distance from L2 is at most 1 plus epsilon. So I want to draw your attention to the Banach-Mazur distance here, as I've been saying, T, as on the previous slide, is a linear map. So in particular, this means that that we can surround the bow of the subspace E by two ellipsoids, one multiplied by 1 plus epsilon. In fact, one can always get subspaces such that we have the little bit stronger inequality. So the map T here is a multiple, is the lambda times identity map. It might be that the subspace will be of smaller dimension, but what I mean here is just that every ellipsoid of dimension, say 2n plus 1, has a subspace which is almost spherical of dimension n. So that's how I can always go to this to this sort of almost spherical section rather than almost ellipsoidal section here. This will be important because this property here, I'll be referring to it as a subspace being strongly almost Euclidean, but I'll come back to this. Okay. And here one has to, of course, mention a very influential second proof of this theorem by Vitaly, who's also the author of the question that we've been working on. Okay, so the title then mentions further complemented subspaces. So let me quickly define it. We'll say that the subspace E of a normed space is well complemented if there exists a bounded linear projection from X onto E. But since maybe I will underline it now, that I'm only talking about finite dimensional normed spaces. So here we want to something a little bit more quantitative. So one can say that a subspace is C complemented if there exists a projection onto the subspace E, which I denote by P, such that for all x's, we have the following inequality. The norm of px in our space is at most C times the norm of x, which in particular means that the projection has an operator norm at most C, right? So I'll be referring to such subspaces C complemented. And here comes the question of Vitaly. Let K be a positive integer, epsilon some positive constant, and capital C to be a real number greater or equal than 1. Then does there exist a capital N such that every normed space X of dimension at least n, which is already C Euclidean, so this is an assumption here, admits a subspace E of dimension K, which is both at the same time 1 plus epsilon Euclidean, so the Banach-Mazur distance from L2 is at most 1 plus epsilon, and at the same time E is 1 plus epsilon complemented. Okay, so of course, with the assumption here that the space X is already C Euclidean, if one would assume that and try to prove the Vertsky theorem, then the proof significantly becomes simpler, and it's just like an argument about delta nets and the volume of the spherical cups. But here it is an important assumption because otherwise the statement isn't true, and one can take an L infinity ball, L infinity, which isn't C Euclidean. For C is not a constant anymore; it depends on n, and there isn't such a subspace. But otherwise, this question, I mean, with this assumption, still this question is very, very difficult, and we've been looking for a sort of way of tackling those two conditions together. And therefore, we propose the reformulation of it, or actually strengthening of this question. So now we are asking for a space, normed space, such that there exists its subspace of dimension K. And of course, one can later on wonder about the dependence on K, right? If you would like to prove it in positive direction, one would want to know something about the dependence of K on N and K on C, say. But since I'm going to, as my first slide said, present you a counterexample, I'm not bothered with that. But anyway, so our strengthening of the question is that I'm looking for a subspace E, which is strongly 1 plus epsilon Euclidean. And I mentioned already to you that this means that the map T, the linear map T, is the multiple of identity, so that we have E is strongly 1 plus epsilon Euclidean. If there exists lambda such that the norm of X is between lambda L2 norm of X and 1 plus epsilon lambda L2 norm of X for all X's in the subspace. And moreover, E is strongly 1 plus epsilon complemented if the projection that has a small operator norm is actually the orthogonal projection. So here we are narrowing our options very significantly. And as much as we feel and believe, and I mean, it feels very natural, the first assumption, so strengthening to having strongly almost Euclidean subspaces feels like it doesn't change as much, because as I said, if you have a 1 plus epsilon Euclidean subspace, then there will be a subspace which is strongly almost Euclidean of dimension half of the original one. This is a significant the significant strengthening of those conditions. And we're still working on trying to go back and trying to use our result for those strong conditions and coming back to the original question. But this is work in progress. Okay, so why did we?
Sorry?
Yes.
Can I ask just to be sure that I understand? So here X is realized in its Rn with a norm.
Yes, it is Rn with a norm.
It's that's how you make sense of the two norm and the orthogonal projection.
Yes, of course. Sorry, yeah.
Thank you.
You're welcome. And yes, so why did we choose those conditions? Like the first one, as I said, is quite natural. The second, maybe a little bit more special, but we've chosen it on purpose, of course, and it's because of the reformulation that we have found of those two conditions into a one condition. So here's an important definition. We have a n-dimensional normed space, and we'll say that the point in the space is epsilon good if for all z in X, we have this following inequality. We have that the scalar product of X with Z is at most 1 plus epsilon times the norm of Z in the space divided by the norm of X in the space times the L2 norm squared of X. This is for the scaling properties, obviously. But what does this mean geometrically? So this is just a condition for if I had my unit ball here. This is a condition that realizes this is X. I'm writing X as sort of array, right? So this is lambda X. This condition just says that there exists no Z, which would be, we can say it on the boundary, whose projection onto the one-dimensional space spanned by X is large. So let me write a few more details. So if I say that, if I write the orthogonal projection onto X of Z, this is of course X over the 2 norm of X. I'll sometimes be skipping 2, but a one-line norm will always be Euclidean norm for me. Z X, X over the norm 2 of X. Then if I look at the operator norm of this projection, right, then this is clearly equal to X Z norm of X divided by X2 squared, and the norm of, oh no, that's all good. And therefore, this condition here of X being epsilon good means that the projection onto the one-dimensional subspace spanned by X has norm at most 1 plus epsilon, right? We can rearrange it, and so we want this 1 plus epsilon. Okay, so in particular, in this ellipsoid, more or less that I drew here, this point, this X here, we can always think about the unit points, unit vectors in L2. So this point X here would not be good. I mean, if our epsilon was smaller than the gap here, but for example, a point here, so X prime here would be good, right? Because for whichever point Z I will choose, the projection will have a norm smaller than this. Okay, so why this condition? This condition is great because we have the following lemma. We can say that if you have a norm space X, then the two conditions, there's this equivalence here. If we have a strongly 1 plus epsilon complemented and strongly 1 plus epsilon Euclidean subspace, then every Y, oh, this is a typo, that was supposed to be Z, right? So we can say Z in Z or Y in Z, doesn't matter, is 2 epsilon plus epsilon squared good. And if epsilon is small enough, then every point in Y, if every point in Y is epsilon good, then Y is strongly 1 plus epsilon complemented and strongly 1 plus epsilon Euclidean. And since I want you to get used to this idea of epsilon good points because they're important, I'll give you the idea of how one proves the lemma. But before that, here's the final question, the reformulation that I mentioned, which is, again, just to remind everybody what's the main objective of this talk, is to answer the following question. Does there exist n such that every norm space X of dimension at least n, which is C Euclidean, admits a subspace Y of dimension K such that every Y in Y is epsilon good. So now we have this reformulation. Okay, so let me prove something here. I'll show you this equivalence because it's quite nice, and I want everybody to sort of start feeling a little bit more what those epsilon good points are. So okay, if I want to show, if I have a strongly complemented and strongly Euclidean subspace, then we know what? We know that if I denote by py the orthogonal projection onto y and say y is both of those conditions, then I have that py of any z is less than or equal to 1 plus epsilon times the norm of z, of course. And moreover, this is for every z in x. And moreover, I have that this is the strongly almost Euclidean condition, y 1 plus epsilon lambda y. This is for every y in y this time. Okay, so what those conditions give me? So I want to show that every point is good with some scaling. So I take y and I take some z. So I fix z and I look at what happens here. So I know that this scalar product is actually equal to y and the orthogonal projection of z onto y. And this is less than or equal our favorite inequality, py of z, Cauchy-Schwarz. So now what I can do, I know since this point, the projection of z is already in y, I can use the almost Euclidean assumption, and I can say that this is y times 1 over lambda py of z. Okay. Now this is in turn less than or equal, and I'll incorporate here a term that we want to show up, of course. So we wanted there was a y squared over the norm of y, so I need to now multiply by it again. And I have the 1 over lambda, and now I know that the norm of the projection is at most 1 plus epsilon times the norm of z. Okay, and we're almost there. We just need to get rid of this term here. And this term here is at most, if we look at our almost Euclidean condition, is at most 1 plus epsilon times lambda. So I have 1 plus epsilon squared because there is this one, lambda cancels with this lambda over here, and we get what we needed, y of y squared z over y. So this direction is the easy one, but the other isn't much harder, but conceptually it's a little bit nicer. So now we are assuming that every point in the subspace is epsilon good, and we want to show that the subspace is strongly 1 plus epsilon complemented and strongly 1 plus 3 pi over root times root epsilon Euclidean. Okay, so we are assuming that for every y in y and for every z in x, we have that x. Sorry, not x. There is no x. Y z. Y z, and this is 1 plus epsilon z y squared. Okay, so what do we know from about this? So let me first start with the strongly complemented subspace. So I know that, so if I look at the norm py of x, this is a vector, or py of z, say. This is a vector already in y, and therefore this is equal to, py z, of course. Okay, this is the same as py z. And now we can use the fact that this guy here is in y, right? Because it's a projection onto y, and so it is epsilon good. So we get that this is less than or equal than 1 plus epsilon norm z over py z times norm z squared, and norm p, sorry, that's p y, z. And therefore, we are obtaining rearranging that indeed this is a 1 plus epsilon strongly complemented subspace. Now, let me erase this. For the almost Euclidean part, okay. For the almost Euclidean part, we will, this is okay. We'll assume towards a contradiction that it is not, so assume that y is not 1 plus, say, a strongly Euclidean. So what does this mean? In particular, this means that there exists some vectors y and w in y, such that the norm of y is equal 1 plus a times the norm of w. Okay, so and we can assume that y and w are unit vectors in L2 norm. So they are on the sphere. So in particular, if I have a sphere, we have like our unit ball of our norm. This means that if I choose y here, yeah, y has a smaller norm than, larger norm than w, because so a, I'm assuming, of course, it's positive. Then what I want to do is I want to find a path of the shortest arc connecting y and w. And of course, since norms, unit balls are origin symmetric, we know that w is not equal to y. So in particular, we can assume that the angle between those two is less than pi. And we can find the shortest arc between the two and partition it equally into vectors between. So I will say that w is equal to, say, x0, and then I'll have x1 and so on until xm, which will be y. Okay. And then by the pigeonhole principle, we get that there exists some I such that xi has norm less than or equal than or times, because we're going from w to y, therefore these will be larger norm, a plus 1 to 1 over m is less than or equal than xi plus 1. Okay. And so I want to say that we can now choose m such that xi plus 1 is a witness for xi being bad, so not good. Okay. So what does this mean? I'm looking at the expression of the epsilon good point. So I need to look at the scalar product of xi plus 1 and xi. And here I have the norm of xi plus 1, because I want xi plus 1 to be the witness. By witness, I mean this will be the point for which the inequality doesn't hold, of course. So here I have xi, and I have the norm of, up here, the norm is on the bottom, xi plus 1 squared. But since I assumed so, actually y and w, and I drew a wrong picture, but what I said is that they should be of Euclidean unit norm, and the same for the x's. So this is more than the cosine of the angle between xi plus 1 and xi, times what we get from inequality here, star, that this is at least 1 plus a over 1 to the power of m. And this, with a little bit of calculation, you can show that this is at least 1 plus a over 2m. And if we choose a appropriately and m appropriately, of course, then we showed that xi is not a over 2m good, which in turn gives us this lemma. Are there any questions here? No? Okay. So our theorem, here I'm stating it, it says that there exists a norm. So first of all, there exists constants epsilon and c, such that for all sufficiently large n, there is an n-dimensional norm space, which is C Euclidean. In fact, it will be 2 Euclidean, which does not contain any 2-dimensional subspace, which is both strongly 1 plus epsilon Euclidean and strongly 1 plus epsilon complemented. And here is our example. It has quite a easy formulation. So this is our norm. I hope I managed to be, I changed the norm everywhere. I decided for the 3-line norm so that it really stands out. Is defined as the sum of the this is like an ellipsoidal norm. So A here is a matrix, which is a sum of an identity matrix and a random orthogonal projection of rank n/2. So this is sort of like a randomly rotated ellipsoidal norm, right? And we're adding to it a tiny portion. So eta will be an absolute constant, but it will be really, really, really small. A tiny portion of appropriately normalized L1 norm. So you can imagine, you know, there is the rotation, the random rotation of the big ellipsoid, which gives us sort of in some sense main understanding of how the space looks like. But then there is this slight, this really small perturbation of this norm. Let me just address one thing immediately. Since this norm is really similar to a norm which is basically an ellipse, like whose unit ball is basically an ellipsoid, which means that it is really 1 Euclidean in the sense of Banach-Mazur distance. This example does seem like a very bad example to consider when you want to attack the original question. But it's a good example for us because, as I'll show you soon, all those epsilon good points are arranged along the eigenspaces, which in this case are quite nice, right? Which means in particular as well, if the epsilon good points are only around those eigenspaces, it means that the volume of them is very small. But good news is that we've found norms which have a symmetric basis and also still have few epsilon good points. Because of course one can now start wondering, can every norm have a lot of epsilon good points, and then you're basically done. But this is not the case, and we can find also like candidates for a counterexample to the original question. But we work with this case because it's very nicely differentiable and it's generally in a nice space, and those epsilon good points are really nicely arranged, which we'll see what this does later. Okay, so this is our norm, and now I'll go on and try to show you some elements of how one proves that this is indeed a counterexample. Okay, so to start with, let me remind or let me define what I mean by a support functional of a norm. I say that f is a non-zero linear functional, support functional of a norm of a norm at x, if for every y which has smaller norm than x, we have that f of y is just less than or equal than f of x. This is because I want to consider those multiples because this is a handy thing for me. I know that some people like it to be one chosen particular support functional. I'm sorry for you guys. But yeah, so here's a proposition that allows me to talk a little bit better about those epsilon good points, because I mean, you could see I was talking about this projection onto the one-dimensional subspace. So in particular, one is thinking, okay, maybe I can just look at sort of a derivative where the norm is differentiable, and that sort of will exactly tell me something. But sometimes we don't have the differentiability. And therefore, here is a proposition that allows us to deal with this situation. So if I have a space X, which is a normed space, of course, and it's Euclidean in the stronger sense here, but this is not the most important thing, then we have the following equivalence. So for every delta, there exists an epsilon such that if X is epsilon good, right, then there is point Y, which is close by, has the same norm as X and is close to X itself. And there exists Z, which is a support functional for y, such that the difference between y and z is also very small. So this is the situation again with this one-dimensional picture. You can imagine it quite well what this means. But also conversely, we have that for every epsilon, there is a delta such that x is epsilon good if there exists y and z such that x minus y is small, and the support functional, and the z being a support functional for y, which is also has a closed norm to y itself. In particular, we can always talk about points being on the unit Euclidean sphere, and then of course, you know, that's what I'll be doing here. Okay, so having this proposition, let us start analyzing our proposed normed space. So one can easily calculate the support functionals. Wherever the norm is differentiable, then it is very nice. But when it isn't, then we need to write, I'm writing the sine of x to be a multi-valued function that takes t to 1 if t is positive, to -1 if it is negative, and to any element of -1, 1 if t is equal to 0. So that's how I'm dealing with this non-differentiability issue. Yes, and later on I'll be writing sine x for x in Rn to be the result of applying this sine defined here pointwise. Okay. So now we know how the support functionals look like, but what does that mean for us? So putting it together with the proposition that I showed you before, we know that x is an epsilon good point, then there exists a unit, so x is a unit vector and it's an epsilon good point. Then there exists a unit vector y and some scalar lambda, such that y minus x is less than delta. And also we have this is this support functional, this is that z I was mentioning, minus lambda x is less than delta. And I'll be writing in a sort of convenient way. I hope you will agree with me that I can rewrite this as the vector being approximately up to delta equal lambda times y. That's what I'll be saying. Okay. So now let me recall what A was and what our norm here was. So A is the sum of identity and this random matrix P. So writing Q to be the difference between identity and P, we get that we can rewrite here the left-hand side, slightly reshuffle, of course, and we get that the sine of y, this function, slightly rescaled sine of y, has to be up to delta equal to some constants, which we can control actually. But here we have py and qy, which means this here is at most 4-dimensional subspace. And this is the main observation that led us to the proof. Namely, it feels quite unlikely that vectors of the form sine y can fit into 4-dimensional subspaces. And let me make this statement a little bit more precise. Oh, so this is just a rewrite of what I said. So the sine of y must be close to a sum of pw and pqw, where w is a 2-dimensional subspace but consists entirely of epsilon good points. Okay. So here is how, like, main elements of the proof. Here is a recollection of what our norm is. And the point number one we've just showed is that if W is a 2-dimensional subspace, which consists entirely of epsilon good points, then for every x in W, there will be a y which is close by, and such that sine y is close to this subspace PW plus QW. Now, the next thing that we are using is that every epsilon good point must be close to PX or QX, which is something that I've already mentioned, which is the fact that epsilon good points will be only close to the eigenspaces. And let me give you an idea of how the proof goes. Okay, so here is this lemma in more precise terms. So let me write what we just saw is that lambda y must be approximately up to delta be ay over. So I will be writing norm ya to be ay y, so this ellipsoidal norm, just a little bit shorter, plus eta and the minus half sine y. Okay. So then if we want to look at the distances of x and pq, say, px, sorry, then this is at most, we can use our way about which we know a lot. So this is at most using triangle inequality, dy px. Okay, but this is at most. So we know that x and y are at most distance delta from one another. And this is the distance between y and px is exactly y minus py, which is exactly delta plus qy, the norm of qy. Therefore, what we need to do now is to minimize the expression sort of qy, py, right? If we write the same thing with a q, that's what we get. So we need to minimize this. So since we have that, it's not hard to see that the norm of ay is greater or equal than this funny norm, this ellipsoidal norm of y, and since the vector here, the eta n to the minus half sine y, has a norm at most eta, of course, then we get an information on lambda over here. So we can see that lambda must be more than or equal than 1 minus eta minus delta. And from this follows that ay minus lambda ya must be less than or equal than delta plus eta times the norm of y, a, which is at most square root of 2 delta plus eta. So this exactly is the statement that I told you, that y must be now an approximate eigenvector of a. So it remains to show in this case that the approximate eigenvectors are close to the real eigenvectors, which of course is not always true for general linear maps. But it's not a difficult task. It's like it's a little calculation. One just rewrites. One uses the fact that, let me write here, that ay is equal to 2py plus qy, right? Because of the definitions of a, p, and q. And we can write it that ay minus ty, so now t is any parameter that I want. This is equal to 2 minus t squared py squared plus 1 minus t squared qy. And rearranging, slightly changing, making a small change of variables here, one can show that we must have py, sorry for the small letters now, py squared less than equal than some constant, which turns out to be exactly this expression squared, and the same for qy, showing the claim. Okay, so now we know where in our norm the epsilon good points are. Are there any questions at this point? Okay, so now we know where to expect the good points to appear and where we need to really work hard. So I showed you, so we showed 1, we showed 2, more or less. And in the next step, what we do is we use claims of this kind. Every point which is close to one of those random subspaces of dimension n over 2 has coordinates that take several different values, but they also have a large support, right? So now let me check the time. I have 10 minutes. So maybe I'll show you one example of, or I'll show you both examples of dilemma. Maybe I'll prove just one of them. So a lemma of this kind. If k is a positive integer and c and gamma are positive constants, letting Y to be a random subspace of L2 of dimension M. So Y is of dimension M. Then the probability that Y gamma contains a unit vector X with at most k distinct coordinates is at most this magical expression here. And this comes from, those claims are sort of combination of probability and combinatorics a little bit, because what one can do is here, for example, we say that, okay, so the number of partitions of the set 1 to k into k sets, is at most, let's say, k to the n, being very, very crude. So this is this k here, k to the n. Okay, then we know that every, so this was say 1, 2, we know that every k-dimensional subspace, so since Y is k-dimensional subspace, has a gamma net. So this is the net argument. I hope everybody is familiar with gamma nets. That means that this is a set of points in Y such that every point in Y is at most gamma away from one of the points in the net. Has a size, so k-dimensional subspace has a gamma net of size at most 3 over gamma over n. This is standard argument over k, sorry, to the power k, because it's k-dimensional. And now what we can do is to say that the probability that we want, so that the Y gamma contains a unit. Sorry?
Can I ask a question? I don't understand what is n in the first sentence.
What is n in the, of this, sorry. So first, this n here.
Yeah. So
we have a Y is a subspace of, so this is R2.
No, but you have partitions of one set from 1 to k into k sets.
Yes, that is something.
I think there is some misprint there.
I think you are right. I think you must be right. So I probably just want partitions of set 1 from 1 to n, because I want distinct coordinates, but we are still sort of, our subspace is a subset of Rn. Thank you so much.
And probably in part 2, don't you need m-dimensional, since you have an m-dimensional subspace?
Thank you very much. Yes.
Sorry.
Very sorry. This is m, indeed. Okay. Okay, we're getting there. Thank you so much for helping. So now what I want to say is that the probability that Y gamma contains a unit vector X with at most k distinct coordinates is at most the probability that Y2 gamma contains a point in one of the gamma nets, right? So contains a point in one of the nets. Okay, and this can be shown also again by sort of standard volumetric argument of you can now fix a subspace and instead look at a random vector and say, there is the again gamma net of the subspace, and the spherical cap around the point has volume at least say 8 gamma to the power of n. That actually is, so like c times c to the n times gamma to the n minus m. Sorry, this was quick, but so I'll just write it. We need to multiply what we got here. So there's the k to the n, there is the 3 over gamma to the m. So why I get m k-dimensional subspace? No, sorry. So here this m, I wasn't clear. I do want k. I don't want m. I do want k. But now I'm explaining myself why. I'm looking at the gamma net of the subspace. So if I chose one partition and I have a subspace that consists of points with k distinct coordinates, this will be a k-dimensional subspace, and I'm looking at the net of this subspace. Okay, so I want here k, and there is this sort of constant. I claim c to the n gamma n minus m is the probability, or actually two, because I need to be within 2 gamma from my subspace. Because if I'm within gamma from a gamma extension of within gamma from y, right? So so this is my y. Now this is my gamma extension. So here is the distance at most gamma, and here is distance at most gamma. Then my point is here. Then if I choose any net gamma net within y, then this point will be within 2 gamma from a point in a delta net. So that's my claim. And this is the sort of estimate here. I'm sorry if this is a little bit unclear. I hope so. The c to the n, one can work it out, and it becomes it can be done to be 24 to the power of n, and that gives me the claim. Similarly, this is the fact about those cups that I've wanted to show. Sorry. Then a different claim, the one that I mentioned to you about having a small size of the support. I mean, this is again very similar argument. You sort of now estimate the number of sets of size at most r, which is n choose r, and s at most 2 to the n, and then you do basically the same thing. And the corollary of this lemma is that the projection P that I've chosen, the random orthogonal projection of rank n over 2, and the Q that is defined as identity minus P, can be chosen with high probability to contain only vectors whose support size is more than n over 4. So what I wrote here is actually that the probability that either of those extensions, 2 gamma extensions of px and qx, contains a vector of support size at most n over 4 is very small as n goes to infinity. And this is important to us because we'll be using it to obtain contradictions at next stages. So let me briefly, I think I have 2 more minutes, so I'll try to just tell you what happens. So I hope I more or less ticked off this one. I hope you believe me. And then, or hope you don't believe me and you'll read my paper to actually check it that I was right. And the last thing that we are using is that the claim that I've mentioned already, that the signs of y, that those vectors which are sign vectors, do not fit approximately in a 4-dimensional subspace. So what we do here to analyze it is we consider typical vectors in a 2-dimensional space. So now choose a 2-dimensional space. We can always reparameterize it so that it's expressed as Ri sine theta plus phi I, where our R's and phi's are fixed, and theta is the parameter with respect to which we are parameterizing, of course. And now what we are doing, since we start having issues where the coordinates are very small, right? Because if the coordinate is very small, then sine becomes the whole interval between -1 and 1. So to take care of it, we consider a subset of large coordinates where alpha is chosen later at just some parameter. And we consider just the coordinates which have this large norm. And we call a point typical if the number of coordinates which are small is less than a certain number. And one can show that this happens with quite high probability. And this is just a condition which is here for convenience, which just means that we will, and it holds with probability 1, that will never, like the sum of phi and theta I will not be 0 or pi, so that this does not become 0, of course, any coordinates. So using those typical vectors, what we are doing is we're considering a set of all the vectors of this form. So we are looking at the large coordinates of the sign vectors, so where the sign vectors of x theta is well defined and is a 1 value. And then we consider a beta separated subset of it, which which is the maximal centrally symmetric in beta. In particular, it is a beta net in sigma here. And consider cases. So I'll only tell you now 2 sentences, is that we consider cases on size of a V. And since V is centrally symmetric, we'll always have a point and its antipodal. That's why the size of V here is 2k. So if k is equal to 1, then we are able to obtain a contradiction with the fact that the extension of the 2-dimensional subspace does not contain a vector of support size less than n/4. This is because if W had only epsilon good points, of course, because it has to be close to the eigenspace. And then we know that close to an eigenspace will always have a large support because it was a random subspace. If k is between 2 and 4, then we can obtain, and this is the hardest actually case to analyze. We obtain a contradiction with the fact that px gamma and qx gamma do not contain a vector with at most 5 distinct coordinates. And in the case when k is larger than 5, greater than equal than 5, then we just show, and this is actually the easiest case, we show that the set of sign vectors does not fit into the 4-dimensional subspace in quite straightforward way. Okay, thank you for your attention. I hope I started speaking fast towards the end. I'm sorry for that, a bad habit.
Thank you, Kasia, for a very interesting talk. Are there any questions or comments from the audience?
Well, I have, can you hear me? I
Yes.
have a question, which is, first of all, thank you very much for this lecture. And the question is not directly related with what you said, but it's definitively related with local properties like the one you considered and the Gauer's dichotomy theorem. So it's rather maybe more than a dream than a real problem at this moment. Is there any chance to obtain a theorem of the Gauer's dichotomy type for local properties? So let me try to be a little bit more precise. Would there be any chance to show that given a separable Banach space, there is always a subspace in which you have very few projections, say a Pizier space in a certain sense, or a subspace where projection.
Sorry, I can't hear anymore. Is that me or is
People
that?
may have an opinion of this in the audience as well. Is it totally unrealistic to have this type of dichotomy, or do you see any make it work?
I'm sorry, we didn't hear the question, I'm afraid.
So Gilles, we missed the very last part of the question after you talked about PZ.
Okay, let me try again. Maybe the technique is fighting against us. The idea would be to hope that a general result, general dichotomy of this kind could be true, that any space would contain either a very bad space in terms of projection. I'm thinking of the type of spaces Gilles constructed, or a very good space in terms of projections, that is more or less a weak Hilbert space. So probably this has to be checked a little bit more carefully, but do you see any chance for such a result to be true?
So actually, there was a moment where we thought we thought we found a counterexample to the original question, and we thought it's so strong that it actually only involves the projection, that you can abandon the almost Euclidean part. And I think that's what you're asking, more or less. And we started believing it, that one could find a counterexample so that every projection is really bad, that has large operator norm. But then it turned out that, unfortunately, doing a few more calculations, this wasn't the case. I think my answer to your question is that I think it could be possible, but at the moment I don't have any better proof than that once I thought it should be the case.
Okay, thank you. Thank you for your attention and for this lecture. Thank you.
Thank you.
Okay, I have a question. Thank you for the talk, very nice talk. Do you know that your example is not a counterexample for the original question?
Well, yes, because in the original question, you ask about Banach-Mazur distance being at most 1 plus epsilon, right? And the projection being bad. But then therefore you can scale the norm so that the ellipsoid becomes a bow. And that scaling, so you add to a unit bow, basically just a L1 norm. And this unfortunately is not good enough. Because I mean, the random subspace does not have any properties. It's any subspace is the same.
Yeah, thank you.
You're welcome.
Are there any other questions or comments? So if not, let's thank Kasia again